Let's take a look at lesson 3.1.5. It's all about single, double, triple bonds and energy. So first it wants us to open an Odyssey simulation. So in Odyssey, it wants you to go to simulation 36, but it's actually number 35 on mine, energetics of a covalent bond. These are chlorine atoms, and notice over here it says the distance between them right now is 650 picometers. And so as I bring this slider bar over, I can see the atoms getting closer and closer and closer and closer. And the way that I think this is related to energy, the first question here, is that energy is actually released when two atoms form a bond. And that's based on their location in an electric field becoming the most stable, the most desired. So it's sort of like if you're holding a brick above a table. We talked about how if you lower your hand, that you're actually decreasing the potential energy between, when you drop that brick. So the same sort of a thing is going on with atoms. As they get closer and closer together, they reach this perfect point and they release energy because now it's a more stable situation. And some questions that I have, it said to write 3, are what is the perfect distance? Because it doesn't really tell you. Maybe 160 is the perfect distance, but maybe that's too close. And I would also be curious to know about what forces are involved. So they're not really showing, how strongly these two atoms are attracting versus repelling. And I would also say, why is the energy staying at 0 here? Because I would have thought that it would show something there. It kind of seems like that's not working, but I'm not sure because I haven't seen this before. Next part, it says that we're going to draw some Lewis structures. And the way that you do this is first start drawing the dots around each. So chlorine has 7 dots, and since this is chlorine 2, you'd want to put the other chlorine with its lonely electron right next to it, and you can see that they're going to share their lonely electrons there. The structural formula would include a line instead of those 2 dots. You still need to draw all the lone pairs here. Oxygen has 1, 2, 3, 4, 5, 6 dots. So I'm going to draw another oxygen, 1, 2, 3, 4, 5, 6. So a better way to draw this then would be to have both sets of the unpaired electrons facing each other. So here's a lonely one, here's a lonely one. Kind of going against the rules of our original drawings here. And so we're going to show that there is indeed a double bond between these 2 oxygens. Nitrogen has 5 valence electrons. 1, 2, 3, 4, 5. So 3 lonely electrons. So right away I'm going to go ahead and I'm going to face the 3 lonely electrons all next to each other to show that they're going to form a triple bond. And so when I rewrite this over here, 3. Sometimes I'll draw the dots on the ends of the lines. That's not really necessary. I like to do that to show where they came from. But again, not necessary. C2H6. Carbon's got 4 valence electrons. So I'm going to draw the 2 carbons next to each other. And then it looks like the hydrogens will fit in very nicely all around. So a better way to write this out would be using the lines. So we've got each carbon having 4 bonds. And the last one here, C2H4. Now the carbons are going to have to create another bond between them. I'm just going to show that by connecting them. And I know that because there's only 4 hydrogens here. So I'm going to just rewrite this one over here. I didn't do a good job with my Lewis dot diagram on that one. There we go. Now it says we're going to explore a mathematical model for bond energy. And it says just go ahead, click on the application and play around with it. Let's look at some of the questions that we're going to have to answer here. It says move your oxygen atom closer to the other oxygen atom. Notice what happens when the force arrows and the force arrows and the energy graph when you move them closer together. And then it's going to ask us about their potential energy and a difference when we look at 2 argon atoms. Okay, so here's the simulation. I see that I can drag this neon atom, whoa, closer to the other one, and there's a little energy curve here. So let's choose some different atoms. Let's go right to the oxygen and the oxygen. Ooh, I can't see the whole graph, so I'm going to zoom out here. I see. So as the atoms get closer together, there's this dip in potential energy because right here is the lowest possible energy, so that is the length of the bond. And if I try and bring them closer together, that's just not good because that energy goes way up. And let's take a look at the forces here. So as they get closer together, I start to see some attractive orange arrows. So the nucleus of one atom is attracting the electrons of the other, and vice versa. And then as they get really close together, I see that there's a repulsive force. So the nuclei of one, which is positive, is repelling the nucleus of the other. And then let's take a look at what happens when you see total force. All right, and then let's do what they were talking about with a neon and an oxygen. So these will not form a bond. Oh, I see. So if you take a look at the graph above, there's no dip in potential energy here. It says describe at least 3 observations when you're moving the atoms close together. So we can say there is a dip in potential energy at the perfect distance, which is just the bond length. Another observation is that the attractive forces show up first, attracting those atoms together, and then the repelling forces show up when atoms get really close. As the 2 atoms get together, what happens to the amount of potential energy? It decreases. What type of energy transfer or transformation do you think can account for this change? Well, it must be some sort of transformation. We haven't really learned a lot about the specifics yet, but we're going to see in chemistry when new bonds form and energy is released. A lot of times it's released as heat or light. We've seen that a little bit already when we were in our combustion unit. So that bond energy, it gets released and transformed from potential energy into thermal energy and light energy. It says, compare the oxygen model with the two argon atoms, which will not form a bond. What difference did you notice? I guess we did argon and oxygen, but same thing. There was no decrease in potential energy. Which makes sense because two argon atoms already have their octet. So there's no more favorable position for them to be in, helping each other out. All right. Now it says go back into Odyssey and use the plots button and plot the distance between the atoms and the relative energy and create a scatter plot. And then it says you can go ahead and move the atoms closer together and further apart. Write a caption for the graph based on your observations. So let's go ahead and scroll down to the directions here. We can add a plot, add plot, XY. It said we wanted to do the CL distance versus the relative energy. Choose scatter plot, it said. So I'm going to go ahead and start dragging these. Oh, I guess that's just rotating them. Got to use the slider bar here. Dragging these atoms closer together, and I'm following the yellow dot on the screen. Now I'll be able to find the perfect distance here when I get to the bottom. Oh, it says right here. So 205 picometers seems to be the bond length between the two chlorines, because if I put them together even more, then they're not at their lowest possible potential energy. So 205 picometers. 205 picometers is the perfect distance to decrease potential energy the most. The distance between the atoms that results in a minimum is called the equilibrium bond distance. It's the average distance between the two atoms. Oh, we just did this, 205 picometers. Then it says scroll down the right-hand side until you see the radio buttons for the abstract representations of the chlorine molecule. Try each one to see the different models that can be used to represent the molecule. So we're going to look at the original electron density, ball and wire, ball and spoke, and space filling. So going down here, ball and wire. Oh, it kind of looks like a diagram that we've been drawing. Ball and spoke gives you a little bit more depth of the atom. And space filling is another way of showing you that electron density. So a benefit, you can still see the nucleus of the atom with just kind of that faint cloud. A drawback of it is it's not as simple. The the ball and wire was very simple. And I would say the opposite, the drawback is, where are the electrons, question mark. The ball and spoke is also simple. I feel like that's what we're accustomed to seeing a lot of times too. Again, a drawback is where are the electrons. It's not really specifying the electrons versus the nucleus. And the space filling, the benefit is that we definitely see the electron cloud, but the drawback is we can't see the nucleus of each atom. It says nitrogen molecules are also made of two atoms that come closer and closer together. It says there are ones that allow you to see the nitrogen atoms at various distances. Use NN distance. Okay, so we're going to plot NN. Let's see. So here is the two nitrogen atoms. So let's plot the nitrogen distance versus the relative energy. And let's take a look here. Is there a way? Maybe you just have to click through. Oh yeah. Oops. That's not what I meant to do. Okay, we can see it now. So as I click, try and find the lowest possible distance. Is it 110? There we go, 110. So with 110 picometers, I see the yellow dot at the very lowest. So the nitrogen bond is much, the bond distance is shorter, which kind of makes sense because they said it's a triple. So 110 picometers, it's a shorter bond length. All right, hopefully that gives you enough so that you can take it from there and finish the